So you're trying to figure out, so we're doing backwards of derivatives. We're doing integrals. And integrals can be used for a variety of things, but one of the main things they can be used for is summations. Okay. By the way, Shannon, how much of that Thanksgiving thing did you get on video?
None of it.
Ah,
Sorry.
there's my YouTube fame just vanished. No. I guess I have to keep this job a little while longer. Okay, you can start whenever you're ready.
I did.
Okay. Probably just as well. All right. So you can use integrals to do sums, summations. Okay. So why would you care about sums? Well, you want to add things up. That's what a sum is. And lots of times you want to add up lots of things. For example, you're going to price stocks in finance class. Stocks are discrete. And you get pieces of stock, and they issue dividends. And one of the ways you come up with a long-term valuation of a stock is sort of extrapolating what you think its dividend stream will be over a period of time, and then using that to calculate the price. So what does that mean? Let's say you have stock in something ordinary like Verizon. Verizon issues a quarterly dividend, you get a check. If you have 100 shares, you might get, say, $4. And $4 a year. Okay, it's not a lot, but remember, if you have 1 million shares, it starts to turn into real money. And then you get that every quarter. You get your share of Verizon. And its dividend, in theory, will go up. It will go up with inflation, and it will go up because Verizon will do better. Fix the microphone now. And then you want to add this stream of dividends up. So GE announced today that they're going to be reducing their dividend. That's going to dramatically affect GE's stock price because either the dividend's going to go down for a period of time, it's going to be lower, or it's just going to have a blip. If it's just a blip, it doesn't really make much of an effect because GE is a 120-year-old company and it's probably not going anywhere. But if you think it is going to have problems, then that's what you do. So you can add up the stock prices. Now, because these are what they call discrete, you only get them quarterly, you don't need to use an integral. You use an integral when you want to add up an infinite set of these. Okay? However, you could use an integral, and the truth is you can probably get pretty close either way. If you're doing General Electric, this thing does not want to stay on. So how do we add things up to do approximations of an integral? So one of the problems you have with integrals is you can differentiate anything, but you cannot integrate anything. There are many functions that you can't integrate, and so you use approximations to figure out what the integral would be. And one of the ways you do the approximation is by doing a sum of rectangles. So, as I said last time, suppose you just have a curve. And you want to find the area under the curve and the x-axis. You want to find this region. You could say, well, I know that if I take a rectangle here, and I find the area of that rectangle that's less than the area of the region. So that's not very good. But I can bracket it by doing the rectangle above and the rectangle below and sort of going halfway between them. And that'd be about right. So I could do better by doing more rectangles. So I could say cut this into a pair of rectangles, which means my error is this region. I'm not adding up that region. You say, okay, instead of a pair of rectangles, we do 4 rectangles. Why don't I cut it into 4 rectangles? So how do you find the area of a rectangle? The area of a rectangle is base times height. So I take this region and I cut it into 4 identical intervals. Now that'll give you the base of each of these rectangles. To find the height is the y value. So what I do is I take one of the 2 points in the interval, either the left or the right point. So I'm going to take the left point and go up to where the curve is, and I use that to establish the height of the rectangle. Then I go for, say, I have all these intervals. I go here, I go up to the curve and across, like this. Okay? That gives me 4 rectangles, and if I add up those 4 rectangles, the areas of those 4 rectangles, I'm starting to get close to the area under the curve. I'm still off, right? Still got these little regions under here that are less. But then if I did this again and I did the rectangles above the curve, I'd probably get close. Now, how would I do rectangles above the curve? You take the interval, and instead of going to the left side of the interval, going up until you hit the curve and going across, go to the right side and go across. This. Okay? Now I'm overestimating the area. And if I average the two, I'm going to start to get pretty close. So let's see how we would do that mathematically. And then instead of 4 rectangles, of course, if you do 8, they'd be thinner. But I'd have to add up 8 of them, and then I could say, well, why not 8? Why not a billion? Okay? And then they'd be very, very thin, and there'd be a billion of them, but then I would have a very tiny error. Yes?
So when it's underneath the curve, that's left. When it's go above, then it's right.
Well, the question is, when it's under, is it left, and when it's above, is it right, if the curve is going up? If the curve is going down, it's the other way around.
Okay.
So you just, for now, you just think about using the left side of each interval and the right side of each interval. So when I say interval, well, let's pick a curve, like y equals x squared plus 3. So first of all, what does that look like? Well, that's a parabola. And since we're only concerned with the first quadrant, we go to 3, and it just kind of goes up, just like those pictures. And do a slightly better curve, make a mess at the board, like that, okay? And I'm going to find the area under this from x equals 0 to x equals 4. So I want to know what's the area under that. Well, this rectangle is 3 times 4 is 12, so it's certainly more than 12. And 4 squared plus 3 is 19, so it's certainly less than 4 times 19. So it's somewhere in the middle. So say, okay, so I'm going to use 4 rectangles. 4 is a nice number. It's not too stressful. So I'm going to cut this x-axis at 1, 2, and 3. Now, how am I going to find the rectangles? Well, let's see. Well, first of all, when x is 1, 1 squared plus 3 is 4. When x is 2, 2 squared plus 3 is 7. When x is 3, 3 squared plus 3 is 12. So now I have what will be the heights, okay? And I say, all right, I take this first interval from 0 to 1. So the width of that rectangle is going to be 1. The height is I go up to f of 0 and go across, and I draw a rectangle. So it's 1 times f of 0, which we know is 3. We'll fill that in a minute. And I say, okay, next rectangle. And you go the left side of the interval from 1 to 2, which is 1, go up to hit the curve and go across. So the width again is 1, and this time it's f of 1. That's the height of the rectangle. You see how I'm getting these numbers? Okay? The x value is, well, I choose to take the interval from 0 to 4 and cut it into that many pieces. And this 1 is the width of each of those rectangles. And the height is found by evaluating the function at the left endpoint of each of those cuts in the x-axis. So the next one, I go up to 2 and across. And then for the last one, I go up to 3 and across. Okay? So to get the height of each rectangle, you're going to use the y value. And the y value is because you're getting the curve, okay? Now I add these up. So what is f of 0? F of 0 is 3. F of 1 is 4. F of 2 is 7. And f of 3 is 12. And I add it up, and I get 3, 7, 14, 26. I said, well, the area is about 26. It's bigger than 26, because I know I'm not getting the whole area. I'm missing all of that. So how can I do better? Well, I said I could cut it into more rectangles. I could cut it into 8 rectangles, or 16 rectangles. They don't have to be multiples of 4. Cut it into 20, 30, 50, 100. You can do it with a computer. You cut it to 100 rectangles. Be very accurate. Be off by a tiny bit. Because imagine this is cut into 100 of these. Every little rectangle coming close to the curve. As you get closer and closer, as you zoom in on the curve, it starts to look like a line. It stops looking like a curve. You say, okay, but I want to do better with just 4 rectangles. You say, well, now, let's do it again. And instead of picking the right end point of each interval, let's pick the left end point t. So I get those y values, remember, by evaluating the function. All right, so now let's do the rectangles again, but let's do the right-hand rectangles. So these are called left-hand rectangles, or left endpoint rectangles, depending on which book you use. We abbreviate that LHR. So if I want to use right-hand rectangles, well, the width of each of these rectangles is still going to be 1. Now, I go across at 1, and then I go to the curve and I go down. And that gives you the height. So the first one's width is 1, the height is f of 1. And now I repeat. I go up to 2 and across. And I go up to 3 and across. And 4. And across. So I've certainly overestimated this time. But let's see what that comes out to. Well, let's see. F of 1 was 4. F of 2 is 7. F of 3 is 12. And F of 4 is 19. Now I get 42. So using right-hand rectangles, or RHR, I get 42. So as I said, so a good guess would be halfway between 26 and 42, which is 34. And we'll do more on Wednesday. And then Wednesday you can come up with the exact number, but we'll focus on doing these for now. Okay? So a good guess is halfway between those two numbers, which, by the way, doing halfway between those two numbers is doing trapezoids, if you were curious. But we'll worry about that later. Somebody understand the general principle? So let's have you practice one. Put this up here. Nobody can see it. Boom. Notice I picked nice easy numbers. Everything's an integer. Of course, this could get messy. You could go, say, from 0 to 1 with 4 rectangles, and the width of each rectangle would be a quarter. You have to start plugging in fractions. And then very rapidly, you say, this isn't fun anymore. And you switch to a calculator or a computer. But we'll do another easy one. So let's say we have the curve, and we want to estimate the area under the curve using 4 left-hand rectangles and 4 right-hand rectangles. And the curve looks just like our other one. This kind of looks like a parabola, because it is a parabola. Okay? So take a minute, see how you do. I should put that in. I mean, it's not automatically from 0 to 4 after all. All right, so let's do this. If we want to estimate the area from 0 to 4, our rectangles are going to be a 1, 2, 3, and 4. Okay? Just like the last problem. That's going to be our 4 rectangles. The width of each of those is 1. The height of the first one, so if we're doing left-hand rectangles, it would be 1 times f of 0 plus 1 times f of 1 plus 1 times f of 2 plus 1 times f of 3. By the way, notice, first of all, we're multiplying by 1 each time, but you could factor that 1 out. Since they all have the same width, you could pull that out. Because we're going to do one in a minute where the width is not 1. And you can simplify the arithmetic. So f of 0 is 2 times 0 squared plus 1. F of 1 is 2 plus 1 is 3. F of 2 is 8 plus 1 is 9. And f of 3 is 18 plus 1 is 19.
What did you do there?
So to get the f values, I have the equation y equals 2x squared plus 1. Okay? So I plug in the x coordinates to get the y values. And I use the x coordinates starting at the leftmost endpoint and counting up until 1 before the right-hand endpoint. Okay? So that's 32. And then if we want to do the right-hand rectangles, it's the same idea, except now to get each rectangle, I go to the right side of the interval, and I go up and across. I said this will overestimate. So we know that the area is more than 32, and now we can find what is less than. So this will be 1. Well, what's the right end of 0 to 1? It's 1. And what's the right end of 1 to 2? 2. And then 3. And then 4. So this is 1 times 3 plus 1 times 9 plus 1 times 19 plus 1 times 33. And let's see, 12, 31, that's 64. So a good guess would be halfway between those, which is 48. Okay, now let's do this and make it slightly more difficult. Because I know you guys want it to be more difficult. Function y equals x squared plus x plus 1. Estimate the area. From x equals 2 to x equals 4 using 4, let's just do left-hand rectangles for the moment. That's a little messier. So x squared plus x plus 1 is still just going to be a parabola shape. And now we're going to go from 2 to 4 using 4 rectangles. So our x coordinates are more annoying. We start at 2, we go to 4, we cut that into 4 pieces, so 4 equal pieces. It's 2, 5 halves, 3, 7 halves, and 4. And then you get each rectangle by taking the left end. So what's halfway? What's the left end of 2 and 5 halves? Is 2. And going across. And from 5 halves to 3, you take the left side. That's 5 halves. And go across. And from 3 to 7 halves. And then from 7 halves to 4. So the width of each of these is a half. Then we have a half f at 2 plus a half times f at 5 halves plus a half f at 3 plus a half f at 7 halves. And what is f of 2? Well, let's see. F of 2 is 2 squared, 4, plus 2 is 6, plus 1 is 7. f of 5/2 is 5/2 squared, which is 25/4, plus 5/2, which is 35/4, plus 1 is 39/4. F of 3 is 9, plus 3 is 12, plus 1 is 13. And f of 7/2 is 49/4, plus 7/2 is 63/4, plus 1 is 67/4. So this becomes 7/2 plus 39/8 plus 13/2 plus 67/8, which is, let's see, 28 and 52 is 80, 119, 186 over 8, or 93 over 4. Okay, that's a messy number already, and of course you can just calculate it. I probably messed up, but maybe I didn't. Okay? If I give it to you in an exam, you won't be able to use a calculator. So either I would say, stop here, okay, where we say something like set it up, or we have to give you easy numbers, we have to give you integers. I don't think it's unreasonable to ask you to square a half, but, you know, this could be x cubed, it could be log or e or one of those things, then you really just can't do it. Okay, and you use your computer. But you get the idea. So it doesn't have to be, they don't have to be integers, it doesn't have to be from 0 to 4. You could go from 2 to 2.1 using n equals 12. Okay, so the width of each of these can start to get very obnoxious, and the y value can get very, very difficult. But let's just have you practice setting one up. So if I give you, so we're going to estimate the area from x equals 3 to x equals 5 using 4 left-hand rectangles and 4 right-hand rectangles. I only want you to set it up. I just want you to show that you can find the correct pieces. Okay? Don't try to calculate it. I don't care when it comes out. Again, x cubed plus 2x is just going up. We're going from 3 to 5, so you're going to want to cut that into 4 pieces. So what's halfway between 3 and 4? 3.5, good guess. Or if you want to make an improper fraction, you add and divide by 2. So 3 plus 4 over 2 is 7, so 7 over 2. 4 plus 5 is 9, so 9 over 2. So 3, 3.5, 4, 4.5, 5. So we'll see if you know what you're doing. Okay. So how wide is each of these rectangles? Each of these rectangles is 1.5 wide. So to do the left-hand rectangles, you have a width of a half times f of 3 plus a half f of 7/2 plus a half f of 4 plus a half f of 9/2. Okay? That's all I would want to see. I don't need you to work out what those numbers are. Because 9/2 cubed plus 2 times 9/2 is 801 over 8. I think that's right. But it could be wrong. Notice though, you could factor out the half. And you could do f of 3 plus f of 7/2 plus f of 4 plus f of 9/2. Okay? So one thing you can do to simplify these, since they're always the same width, is you could factor the width out of the problem, then you don't have to write it once. So if you were setting up the computer program or the more complex calculation, you know, what happens is at some point we turn this into an integral, then taking this out makes life makes life a lot easier. So if we're doing the right-hand rectangles, the width again is a half. But now instead of starting at 3 and finishing at 9/2, I'm going to start at 7/2 and finish at 5. So I'm going to have f of 7/2 plus f of 4 plus f of 9/2 plus f of 5. And again, I don't really care what that number is. Okay? Notice, 3 parts of this are the same. Only the left end differs and the right end differs. Everything in the middle is the same calculation. So once you have one of these, you can get the other. So you can see how there's some sort of error built in, because this one is using a lower number, so you're going to get an underestimate. This is using a higher number. Now, somebody asked me earlier, so left hand is always less and right hand is always bigger. Well, not necessarily. That's what the curve looks like. Suppose you had a curve where you're going down, like that. Okay? Now when you draw the rectangles, well, what? Bad example. Sorry. Going down this way. Okay? So now, the left-hand rectangles are overestimating, and the right-hand rectangles are giving you rectangles that are under the curve. So if the curve is going up from right to left, then left will underestimate it. Okay? And of course we can have a curve that's doing both. Then some of the rectangles will underestimate, some of the rectangles will overestimate. That's why it's nice to have 2 systems, an under and an over. Okay? Because when you put them together, you can usually get a very accurate estimate. And you don't really want a house to always calculate twice. So the other way that you get more accurate is you just do more rectangles. So, we'll just take another example. Go back to our x squared plus 3 example. Let's say I went from 0 to 4, but I wanted to use a lot of rectangles. So 8. So now each one would have a width of a half. 3 halves, 5 halves, 7 halves. So you can see I'm starting to have less error. And then this would be, each of these is a width of a half. This way. And I would have f at 0 plus f at a half plus f at 1 plus f at 3 halves plus f at 2 plus f at 5 halves plus f of 3 plus f of 7 halves. And that would be my left-hand rectangles. So now I have 8 of them. And if I were doing the right-hand side, I'd have a half, that's the width of all of them. F at a half, f at 1, f at 3 halves, f at 2. This gets tedious, as you can see. Okay? So they start to have many more terms in common, and they're only differing by the n term each time. Okay? So this will give me a better estimate just using 8. I could do 16, as I said, I could do 100. But you can make a little computer program. You can do an Excel or your calculator or whatever, and you can do n equals 100. By 100, you're going to be incredibly accurate. You don't really need to do left and right. You can just use left or just use right. And what will happen is algebraically, we don't do that in this class. You say, well, what if I just have an infinite number of them? Then they're infinitely thin, because I'm cutting it into an infinite number of pieces. So, of course, you can't use infinity, but you can take a limit. So you can say, well, let's just cut it into n rectangles, come up with a formula. Okay? The width of each of these is the whole interval divided by n, because there's n of them. The height, well, I'd start f at some value, and then I'd cut it into n pieces, so I have to add all of those up. And then if I take the limit of that, it turns into the integral. So that's what we're going to do. You'll see, we'll do more of that next class. That's the magic jump, is going from doing it in discrete pieces of rectangles into doing it in infinite number of pieces and getting the integral. Just like with the derivative, we would take smaller and smaller pieces of the curve for the tangent line, the secant lines, and then we do an infinitely thin difference between 2 points to do the secant line, and that gives you the tangent line. Right? So these two are linked, which we won't get into, but derivative and integral are linked, and as you saw, when you're integrating, you're doing antiderivative. So this infinity concept links the two of them together, this cutting things into infinitely narrow pieces. Okay, so I can see you guys are all getting a little sleepy, so we'll pick up on Wednesday.